Hello, welcome back to the Computational Genomics Lab, where we're going to do our final differential expression of our peaks between non-treated samples at 0 time point and the rest of the time points using DESEQ with a secret file we haven't talked about yet, 2 secret files that are in the max output that are also in the description below for you to be able to download those and file path to them for this lesson. So today we're doing 05 in level 9. So if we go to lessons, level 9, 05, ATACseq, and DESEQ. And I'm going to go to my environment here and go back up to the top. And what Max did for us is it called every peak. It took every peak that was called in every file and just made one big long file. And it gives us the counts for each of those. So before, when we did DESEQ, we did it on genes and the counts on the genes. Now we can think of peaks or interval IDs as genes. And so we're going to do differential expression between those peak interval IDs with the counts that are provided at each time point. So let's dig in and take a look at that. Okay, so there's much more information in this document talking about that, but here's the other file I'm talking about that comes from the output of max2 broad peak consensus. This is if you ran the pipeline. If you didn't, no big deal. You just need this peak file here, which is freely available to download in the links below. Okay, so we have consensus peak.mlb.cln.annotedpeaks.txt. Okay, so we are going to read that in, that file, just simply doing read.table. And if we look at this, we can see an interval ID, which is every peak that was called. And there's 174,000 of them, because again, it's any peak that was called in any sample, start and end, critical. Now there's a bunch of cool information here, whether it's intergenic on a promoter TSS. So if you wanted to know if it overlapped a gene, you could find it out from this table here. It gives you the nearest distance to the TSS as well. Super handy information in what the nearest gene is to that peak and what gene type it is. So all this information is here. This is a key table that we just uploaded. Okay, so we took a look at that, and we're just going to change the first column. Has this long name here, and we're just going to change it to interval ID. And so if we look at that again, now we see that this column name is interval ID. Okay, column 1 indexed and put in the name as interval ID. And so now we're going to grab the counts table for all those peaks with the same interval ID. So now we have the interval IDs and a bunch of information about them, and a counts table with the same interval ID that we can get the counts for each peak for to make a sample sheet for DESEQ, and that's what we're about to do here. So let's look at that counts table provided to us. It's called consensus_peaks.mlb.cln feature counts.txt, and that means that feature counts was a program that was run on the BAM files to get the counts for that interval, just that one interval, whereas before we did it for genes based on the genome annotation when we did our RNA-seq. Okay, let's take a look at it. There it is. And now we can see that we get counts for each time point. So now we have, for each of our 12 files, a counts value, and we can see some of these counts go up to hundreds of thousands. So interval ID here is going to match our broad peak information, and so we can now know what genes that we're near, but we can also do RNA-seq or DESEQ on the feature counts for each of these peaks, which are listed here. Okay, so let's go back to the document here, and we just took a look at our counts, and so we're just going to we're going to do some cleaning up here because our consensus counts object is a bit weird. And so we're just going to take a look at the row names currently of broad, or we just made the row names of our broad consensus counts the same as gene ID. And if we look at that, which of these is which? Broad peaks consensus counts. And we take a look at it, we can see the interval ID is now called gene ID, which we'll need for RNA-seq, but really that's not the gene ID, it's just the interval of the peak is what we renamed that column. So now we're just going to take out some columns that we want to grab, and we're going to take the gene ID or interval ID, chromosome start, end, strand, and length out of that table with all those features. And so now our broad consensus counts has just the counts, which we need for DESEQ. So we got rid of all the stuff in there we didn't need. So that was dplayer select minus these columns. So we got rid of all those. We just now have our interval ID in meta and our sample name in meta, and that we're following the same DESEQ we did in 05 and 06. Okay, levels 5 and 6. Just going to change the names of these columns because they're kind of goofy. We just want the name of the time point. You can step through this. We're just think of this as find and replace anything that says underscore rep 1, make it underscore R1 to simplify it, and get rid of anything that matches this that's bulky in the file name and substitute it with nothing. And now when we look at our broad consensus, we see a much cleaner name for building a ATACseq pipeline, which we're going to do now. So let's first grab our 0 time points and the rest of the time points. That we'll do that comparison, because if we don't find any peaks there, we're not going to find any other way. So we're going to make a data frame where we're going to have a column called sample, and what we're going to do is an if else, which is cool. So we'll say if there's a match to 0, which is the 0 time points, in the our broad consensus count columns, call that non-docs. Okay, so if else, so if it's true, call it non-docs. Else, if else grep non-docs in the count columns and call those non-docs. So it's just going to label them for us, and we're going to take the time point out of the name and use some regular expression to clean that up as well. So let's just take a look at what we get with this. It'll make more sense. Okay, so what happened there? Object count columns. Aha. So call names is what we want in our count columns. These are the names of our samples. And we're going to go in and do some grepping and cleaning up with those. And now what we see we just made is ATACsamples, the precursor to building a sample sheet. We have the sample name and the condition, which we can factor on for our DESEQ analyses. Okay, so let's do that, where we're going to factor the time points as we have done before. You can go back to our DESEQ, and we can see the levels of the time points here. And we're going to make sure that the columns in our counts are the same as the sample rows in our sample sheet here. Okay, so that's true. We're going to make our DESEQ setup here, where our counts data is going to be our consensus counts, the call data is going to be ATACsamples, and our design is going to be the time points. So in this case, we are doing all the different time points. We can do DESEQ on that, and it'll run, and then we'll do the same sample where we extract the results files, and we'll let DESEQ finish running and come right back. So DESEQ finished running, where it did a comparison of 0 versus 2, 0 versus 4. So we did all the comparisons across all the time points. And now we can get our results using the results function of ATACDESEQ, and we don't want the interval ID as the result. One of the results is this interval, or sorry, my bad. We want to extract the results as a data frame and take the row names to column is called interval ID. And so we take a look at what that makes. We can see what we used to see for DESEQ, where this used to be genes. Now we just have interval IDs, the base mean of the peak, fold change, and p-values, which don't look so good right here, but we won't give it away just yet. Okay, so now we're going to merge our ATACseq, DESEQ results, the DESEQ results on our ATACseq data. And the object we just looked at here is all the intervals with their p-values, et cetera, across all the time points. And we're going to merge that with our broad consensus peaks here. Sorry, that's not it. Our broad consensus peaks, which has all that other information with it. So we're just going to merge these two files back and kind of keep a track of what. Now we're going to add the p-value into this big table of information of what gene is next to it, et cetera, et cetera. And I'm going to clean up here because it's getting kind of busy. And we return back to here. So we're going to just merge those two, and we're going to select it. It'll merge on the interval ID between those two files is shared. And then we're going to just select out the columns we want. These are some handy informations of the interval ID, of course. It's near its promoter, TSS, start and end. And then we will do that by each interval ID. So all the interval IDs will merge and just stay as one column instead of having two columns of those. Okay, so then if we now look at our ATAC log fold change, it should be nice and tidy, and we see the interval IDs, base mean, fold change, p-adjusteds here. If we sort of scan to look, we don't see anything less than, we do see less than 0.05 in the p-value, but not in the p-adjusted, so I would not consider that very good. And then here we're just taking that same document we were just looking at and making them into UCSC coordinates so we can make a bed file of where these peaks are, so we can take a look at them in IGV. And so we're just going to make a column called UCSC coordinates, and we're going to paste the chromosome start and end with a separator of a dash. So that can be plugged straight into UCSC. So now if we look at ATAC LFC, we have this new column that should be at the end, UCSC coordinates, and those can be put into the browser IGV to look at the peak itself. And so if we look at this, I think the news is bad news or good news, depending. We know an answer is that the ATACseq peaks are not changing due to docs. So if we had this, we can see the start and end in UCSC coordinates. We just sort of looked at that. Take a look at the histogram of p-values, not looking good. We don't see in the p-adjusted anything near 0.01. The x-axis ends at 0.99. That's not great. So if we look at the p-value, we see that indeed a couple are significant by 0.05, maybe a couple hundred, and you could look at those in IGV and see if they're convincing to you that there's no peak and a peak, or down a peak and no peak across time. And if we look at log fold change, we do see some log fold changes, but nothing more than sort of fourfold. Most of it is not changing at all. Okay. We could look at the base mean, and but we'll make a results object here to save. It'd be pretty handy, where we're just going to take the results of our DDS again and print the summary of those results. And so I guess we're going to just plot that, use that res. Let's take a look at this. It's our DESEQ results format. We just went back up to what we filtered out of throughout the class. At the very beginning of the class, we had something like this, and if we can use plot MA to look at the MA plot of this here, and we can see that as all the genes that are changing more than a few fold are at the low, like 1 count to 10 counts, which isn't very many. And as you get more reproducible counts, there's none that are significant. So, so that we could plot the PCA between them. But essentially, the bottom line is there's nothing significant. So we could also try now the 0 time point versus all other time points, and let's just do that to see if that could possibly find any. And so we're taking our attack samples again, and we're making a condition column by factoring non-docs and docs now in our attack samples here. Instead of factoring by the time point, we're going to factor by condition, which is docs and non-docs, that second column. So super easy to do this analysis. We can run it and then run the DESEQ the same way we did before, and wait a second for that to finish. It finished running. And so we just basically, we've done DESEQ twice in this class, once where each time point was factored, and now we're just doing 0 versus the rest of the time points. And so we're going to do the same thing, extract our results from that DDS we just ran, and put the row names, make the column name interval ID, and we can look at that. It's quite large, considering how many peaks there are, so maybe it wasn't a great idea to view it. And then we're going to do the same thing and select the same columns from that after we view it. And so we can see a nice interval idea, base, mean, fold change in the P adjusted now for this test, which is different than the previous test. And we can see again, there's no P adjusteds anywhere close. Okay, so let's make an attack LF log fold change matrix data frame based on the 0 versus all other time points analysis. And then the same thing, we're going to just make another column that has the UCSC coordinates for easy viewing. Okay, so there's some things down for here for you to play with. I think we have our final answer, and it was sort of looking like that from our overlaps. Just didn't look great. And if you look at these in the raw data, which we'll look at in the next class, is how this all comes together into one quick document to run. And we'll see you there. But I think for now we know that the doxycycline is not affecting our attack peaks changing through time, but it does affect lots of gene expression, and that's a really cool result. So congratulations, and let's celebrate by looking at it all in one streamlined knitted document so you can show off all your newly learned bioinformatics skills. Congratulations. All right, see you there.